Hi all, welcome to my lecture on probability. In this lecture, I'll be giving a brief introduction to probability and also we'll be discussing a topic called conditional probability. This lecture is just a brushing up of previously learned concepts about probability and also some topics which we have already learned before. The intention of this lecture is to just set a platform to certain concepts that we will be discussing as we progress. Now, where is probability useful? Probability is useful as far as physics is concerned. It is useful in quantum mechanics, statistical mechanics, kinetic theory of gases, etc. And in our daily life itself, we unknowingly or knowingly are making use of probability. And when we are learning the science of probability, there are some terminologies associated with the study of probability theory which we need to be familiar with. And those terms are random experiments, equally likely outcomes, sample space, etc. So let's focus on random experiments. Random experiments are those experiments where I'm not sure of what the outcome will be with the initial state of my system. Uh, that is, when I am performing an experiment, at the beginning, looking at the state of the system, I cannot say how my system will evolve and what will be my final state. I can't say it for sure. Say, consider a very simple case of a coin toss. When you're tossing a coin, you can just you can just make a call that it might be a head or it might be a tail. It can be either ways. If it is an unbiased coin, it can be a head or it can be a tail. But starting with the initial state, you cannot predict that this is for sure going to be a head or this is for sure going to be a tail unless the coin is biased. So, those experiments where we are not sure what the final outcome will be depending on the initial state of the system, that experiment is called a random experiment. And probability theory focuses on random experiments rather than deterministic experiments. Now, we quite often hear something called equally likely outcomes. Now, as the name suggests, in an experiment, you may have several possible outcomes, and yes, we'll learn it with an example. Consider a coin toss. If you're tossing an unbiased coin, it is equally likely that you say that it's equally likely that you get a head or a tail. What does that mean? When I toss a coin, I cannot say that always a head will fall or always a tail will fall. I cannot say like that. It might be a head and it might be a tail, and both are having equal chance to occur. So, those outcomes of an experiment which have equal chances to occur, those are called equally likely outcomes. Or, in terms of probability, you say that both head and tail have equal probability of occurring in a coin toss. So, such outcomes of a random experiments which have the same probability to occur, those are called equally likely outcomes. Now, we always come across something called a sample space. Sample space is nothing but the collection of all possible, mutually exclusive outcomes of a random experiment. Suppose you consider a coin toss. The possibility is a head and a tail. Now, what if you are tossing two coins? Then it's possible that you get a head on the first and a head on the second, head on the first, tail on the second, tail on the first, head on the second, and tail, tail. So, all possible outcomes in random experiments, the collection of all possible outcomes in a random experiment is called a sample space. I hope this is clear. Now, the question is, how do we calculate the probability of any event in a random experiment? So, for that, you just consider there are n mutually exclusive, collective exhaustive, and equally likely outcomes for a random experiment. And small n of them are favorable to an event A. Then the probability of event A is given by small n by capital N. Suppose you consider the tossing of two coins. We just saw the sample space for tossing two coins. We saw it was H, H, HT, TH, and TT. So this is your, from here your N is 4, isn't it? These are the total number of possible outcomes for this experiment. Now, I am looking at a specific event A where my event A is at least one head occurring. So if this is the event then that I am focusing on, at least one head occurring. So out of these 4 outcomes, I see that only this outcome is not having any heads occurring. Rest all, at least one head is occurring, isn't it? So small n is 3, where your small n is nothing but the number of outcomes which favor the event A. So the probability of A would be 3 out of 4. I hope it is clear. So that's what we have done here. If there are capital N number of outcomes in the sample space and small n number favor a particular event A, then the probability of that event A is defined as small n by capital N. And if you're certain that an event will happen, then the probability is 1. And if you're certain it will not happen, then probability is 0. And always probability lies between 0 and 1 because there are cases where you're not sure whether the event will happen or will not happen. So you have intermediate probabilities too, and probability always lies within the range 0 and 1. Now, this is where we'll start with our topic, conditional probability. We'll start right away with an example. Consider tossing of 3 coins. Just before we consider the case of 2 coin toss, here we are considering 3 coins tossed and the sample space is given by this thing. You have 8 outcomes where you have heads on all the three coins and tails on all the three coins and combination of head and tail on the rest of the trials. Since the coin is fair coin, every outcome is equally likely and each one has a probability of 1 by 8. Now, suppose we are focusing on specific events and let E be the event, at least two heads appear, and F be the event, tail appears on the first coin. So if you're writing down the sample spaces for E and F, so just keep in mind E is the event, at least two heads appear. So which means I have to count outcomes where I have two heads and above. So my sample space will comprise of all these outcomes HHH, HHT, HTH and THH. So here is my sample space for E, and F is the event where I get a tail on the first coin, which means I will have this outcome, I will have this one and this one. Again I have four outcomes of the sample space S which favor event F. Okay. Now, is there an outcome which favors occurrence of both E and F? Yeah, of course. There is one outcome, THH, this one. It favors both occurrence of E and F, right? It has a tail on the first coin, which means your event F is favored, and it has two heads. So your event E is also favored. At least two heads appearing. That case is also satisfied. So generally, uh, in the probability notation, we write such events or such outcomes as E intersection F, where your E intersection F just means both E and F occurring. Okay, so the only outcome which favors even both events E and F is THH. Now, what's the probability of both E and F occurring? Out of the 8 outcomes, only one outcome fits in this criterion. So, the probability is 1 by 8. Now, suppose it is given that the first coin shows tail. I mean, event F has occurred. Suppose I am given that event F has occurred. Now, I want to find out, given that F has occurred, what is the probability of event E to occur? Okay, E and F are two separate events. E is at least two heads appearing and F is tail on the first coin. Now I am looking at a case where I am telling you I am being given the information that F has already occurred. Now you look at the probability of E occurring given F has occurred. And this is where we define something called conditional probability, which is mathematically written as P of E given F. Okay. In some textbooks, you also have such a notation P of E given F. Okay. Both these are the same, but we will stick on to this particular notation, which just means probability of E given that F has occurred. Okay. So given that F has occurred means number of events favorable to F. Now out of that, how many events favor occurrence of E also? Is it clear? Out of the number of events which favor F, how many events favor occurrence of E also. That will give me my conditional probability of E given F. So number of events favorable to E intersection F divided by number of events favorable to F will give me my probability of E given F has occurred. Okay, so if you're just dividing the numerator as well as denominator by the number of elements in the sample space, such a such an operation makes no difference to this fraction. So you're dividing it with the total number of outcomes in the sample space. And what is this thing? This is the probability of E intersection F, and this fraction, it's nothing but the probability of F. So your conditional probability of E given F has occurred is nothing but the ratio of probabilities of both E and F occurring and probability of F occurring. This definition is valid provided P of F is not equal to 0. Now we'll understand this concept a little more once we do problems. Let's just do a direct substitution. You are given that P of A is this quantity, P of B is 9 by 13, and P of A intersection B, which means probability of both A and B occurring is 4 by 13. You are asked to find the conditional probability of A given that B has occurred. Also, by definition, probability of A given that B has occurred is nothing but the ratio of probability of both A and B occurring to the probability of B occurring, so which is 4 by 9. If on the other hand you were asked to evaluate uh, P of B given A, it's nothing but the ratio of P of A intersection B to P of A. Given that A has occurred, what's the probability of B to occur? That would be this ratio, and from here you would get it as 4 by 13 the whole divided by 7 by 13, which will give me 4 by 7. Okay, now you move on to the next example. If a family has two children, what is the probability that both the children are boys given that at least one of them is a boy? Okay, so before we attempt the doing this problem, we will just identify our sample space and what are the events that we are precisely looking at. Okay, you're given a family has two children, which means your sample space can be two boys, a boy and a girl and a boy, and girl and a girl. Now, you are asked what is the probability that both the children are boys, isn't it? So let A be the event that both are boys. Now, how many outcomes in the sample space favor such an event? There's just one outcome. So the sample space corresponding to A would be BB, and probability of A would be 1 out of 4, isn't it? Out of this sample space, which comprises of 4 elements, only one outcome favors occurrence of A, so you have 1 by 4. Now, what are you given? You are given that at least one of them is a boy, isn't it? So let's write down the sample space which favors B. You're given that at least one of them is a boy, which means you can have one boy or you can have both the children are boys. That outcome is also possible in this set. So your sample space corresponding to B would be this one, comprises of 3 outcomes. So what's the probability of B? 3 out of the 4 outcomes favor occurrence of event B. So it will be 3 by 4. Now, what's the probability that both A and B occurs? What's A? A is the event, both are boys. And B is the event, at least one is a boy. So, what is the outcome which favors occurrence of both A and B? BB, isn't it? Again, it's just one out of the 4 outcomes which favors occurrence of both A and B. So, P of A intersection B is 1 by 4. Now, the conditional probability of A given B is defined like this, and that's what you are asked to evaluate, isn't it? You are asked to evaluate what's the probability that both are boys given that at least one of them is a boy. So you're given that at least one of them is a boy. Now you're asked to evaluate what's the probability that both are boys. So when you're given such a thing, you evaluate the conditional probability of A given B has occurred, and you evaluate it as 1 by 3. Okay. Now let's move on to the third example. 10 cards are numbered 1 to 10 and they're placed in a box and they're mixed thoroughly. And one card is drawn randomly. If it is known that the number on the card drawn is greater than 3, what is the probability that it is an even number? So, how do I start with? I'll start with writing the sample space, isn't it? What is my sample space? My sample space is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, isn't it? Because I'm told that I have 10 cards which are numbered 1 to 10 and they're placed in a box and they're mixed thoroughly just to avoid any sort of bias in the experiment. And I'm drawing out one card. Now, the question is, I am given that I know the card drawn is numbered greater than 3. Okay. And I am asked to evaluate the probability of the number on the drawn card to be even. Okay. So let A be the event that number on drawn card is even. Okay. So what are the elements in the sample space which favor this event? 2, 4, 6, 8, 10, isn't it? Now what's the probability of A? Probability of A is 5 out of 10 outcomes favor occurrence of this thing. My probability is half. Now, what am I given? I am given that the number on the drawn card is greater than 3. Okay, let that be the event B. Number on drawn card is greater than 3. Okay, so what are the outcomes which favor B? It will be 4, 5, 6, 7, 8, 9, and 10. I have 7 outcomes which favor occurrence of B, and the probability of B would be 7 upon 10, isn't it? Now, what are the events which favor occurrence of both A and B? For that, I'll just have to write A intersection B. Can you just think, what are the events which favor occurrence of both A and B? A is the number on the drawn card is even, and B is this sample space. Now, what are the elements which are common to both these sample spaces? 4, 6, 8, and 10, isn't it? So A intersection B is 4, 6, 8, and 10. And what's the probability of A intersection B? 4 out of the 10 outcomes in my sample space favor occurrence of A and B. Now, can you just tell me what is probability of A given B? It's nothing but probability of A intersection B by probability of B, which would be 4 upon 10 divided by 7 upon 10. It's 4 by 7. Okay. Now, here goes the next question. A die is thrown 3 times. Event A and B are defined as below. A is 4 on the third throw. B is 6 on the first and 5 on the second throw. Find the probability of A given that B has occurred. Can you just think it for yourself? And let's have a discussion post this lecture. Thank you.